So let's think about where we might find these elements. Well, we know stars burn hydrogen, make helium, and we think they can make even heavier things. So let's look at the life of a star like the Sun. So the Sun was formed, we think, about 4.6 billion years ago from a cloud of dust and gas that's hanging over Paul's head. And it collapsed down relatively quickly. And for the last 4.6 billion years, and for another 5 billion years to come, it's been burning hydrogen and forming it into helium for its nuclear reactions. And these nuclear reactions are very well understood, although they're not trivial. So we'll show you what a nuclear physicist would look at what's going on inside of the Sun.
Okay, so you start off with two protons, also known as hydrogen nuclei, and there's a whole network of different reactions. So we combine them with another one to make helium-3, which then can add another one to form helium-4 that way, or helium-3 and helium-4 can crash together to form beryllium. Anyway, a whole network of reactions, all of which different probabilities. So this happens 15% of the time. That one's very rare. This one's 84% of the time. And this has all been studied in great detail, and the end result is producing helium and liberating energy.
So we really understand how the center of the Sun works. Now, it turns out at some point the Sun is going to burn off all of its hydrogen and convert it into helium. So that reaction isn't going to work anymore because there's just simply nothing left inside to convert to helium. And so at that point, the Sun, which is hot, and that heat has pressure, and that pressure keeps gravity from compressing the Sun any further than it already is, the Sun's going to rearrange itself. And when it does that, it's going to start to become denser and hotter. And it turns out that will eventually allow helium to be converted into carbon. And that is another nucleosynthetic process that we understand pretty well. And we're just going to look at it schematically. It really is about taking not one helium, but 3 heliums and making carbon.
This one's a bit tricky. You smash 2 heliums together and you form beryllium-8. The trouble is, beryllium-8 is incredibly unstable. So it normally breaks apart very, very rapidly. You've only got a very brief window of time when the beryllium-8 is still around to crash another helium-4 in there. It doesn't happen if you get another one in there fast enough, your gamma photon is emitted, and you get carbon-12. But if this doesn't hit in that very short period of time, you're not going to get any carbon, which is kind of useful to us. So it can only happen when the density is very, very high, so that there are lots and lots of these collisions happening in the very short time while this is still around.
This is a very famous reaction. It's known as the triple alpha reaction. And it was actually sort of figured out in advance by Fred Hoyle, who said this reaction has to occur because if it didn't, there wouldn't be any carbon in the universe. And it was later figured out that it indeed did.
And everyone at the prior to that told him he was talking complete gibberish, and he said, no, it must be there, and he was proven right. And he then spent the rest of his life coming up with complete gibberish, and everyone else told him, no, that's clearly crazy. He said, but that's what you said last time.
Yes. Well, that's the way science works sometimes. Anyway, the Sun burns helium in its core for hundreds of millions of years. It's going to puff up and become what we call a giant star. So if you've ever seen the star Aldebaran in the constellation Taurus, it's sort of a star in that phase of its life. And then it's going to run out of helium. It'll convert all that helium. You're not going to be able to do that reaction. And that turns out for a star like the Sun to be the end of the road. So in this case, the star is going to rearrange itself, and it isn't able to do any more nuclear reactions. It just simply doesn't get hot and dense enough. And so it ends up in rearranging itself, collapsing down to a tiny little star called a white dwarf, which is about the size of the Earth, but the mass of the Sun. So a teaspoon weighs a ton. And it blows off the outer parts of its envelope into interstellar space. So that's the life of the Sun. Now, big stars, well, they live fast and die young.
Much like rock stars.
So they form the same as the Sun. They form in dust, clouds of dust and gas. But they burn their hydrogen really quickly. They're up to 1 million times brighter than the Sun, but typically only 10 or 20 times bigger. So they have a huge fuel, or a very small fuel tank, comparison to how fast they burn their fuel.
Yes, so an example of this would be like the star Rigel in Orion, big blue giant.
Yep. And then, when they run out of hydrogen, they rearrange themselves just like the sun does. They start burning helium into carbon. And they're going to do this very quickly. They're going to become what we call a red supergiant.
Like Betelgeuse, also in Orion.
Yeah, so Orion is a great place to understand how stars work. You just remember the brightest stars and you get to see it all happening. So the nuclear reactions inside these giant stars, because they have so much gravity, rather than stalling after they make carbon, they're able to go on. And the way they go is they take the carbon and they're able to add a helium nucleus to it. And they can make things like oxygen. It turns out the sun can make a little bit of oxygen. But they can also make things like neon and magnesium. And they can do that because their temperatures are hot, as are their densities. Now, at some point, you're going to run out of carbon. You're going to rearrange yourself. What happens? You get hotter, you get denser. And so then you're able to make neon into things like oxygen, neon, and magnesium. So that's something that the sun could not do, because it's just not simply, it doesn't have enough gravity. Then you can continue on. You can make oxygen and sulfur, it turns out. You make sulfur into silicon, and you need to have very high temperatures and densities to do that. And then eventually you can take that silicon and you can convert it into iron and nickel. And for that you need to be very hot and very dense. But we have a problem.
What happens now?
Well, when we have iron and nickel, we're sort of at the bottom of the nuclear food chain.
Just like we talked about in the talk about supermassive black holes, once you've got iron, you can't get any more energy out. It's the most stable element. That's why it's that peak in the diagram of how much different elements there are. So that's it, star. No more energy to be got out.
So no more energy. And what was holding that star up against gravity? The heat. That heat provided pressure. That pressure balanced gravity. Suddenly the heat source is gone. And it's even worse, because as this thing starts to rearrange by becoming more and more dense, you're actually able to make things heavier than iron or nickel. But that doesn't give you nuclear energy. It takes it away. So you sort of get a runaway nuclear refrigerator. The more it rearranges, the colder it gets, making it want to even rearrange itself quicker. And what we get, well, it's an interesting surprise.
Yes, it's a explosion.
An explosion. And we saw one here in the Milky Way in Australia in 1987, where in the Large Magellanic Cloud, so remember that's a satellite of the Milky Way, we had a little star appear, this little star right here, become a huge explosion that you could easily see with your naked eye. This is what we call a Type 2 supernova. And so these Type 2 supernovae, when we look at them, they make lots of things. So,
yep, so they produce lots of carbon, oxygen, nitrogen, also elements all the way up to iron. Not elements beyond iron, really, but we'll come back to where we produce those elements in another lesson. And they'll produce about 0.1 solar masses of iron.
So it turns out we can tell how much iron they make because that iron isn't made directly. It's actually made in the form of radioactive nickel first. And that radioactive nickel, as it decays, is the thing that helps make the supernova bright. So by how bright these things are, we can gauge how much stuff there is.
When you think of supernova being very bright, people tend to think that it's because of the explosion. You get a brief peak of brightness because of the explosion, but in fact supernovae then get brighter again a second time and stay bright for several weeks, and that's mostly the radioactive decay of elements like the nickel that's driving it.
Exactly. Now, so we see that the sun has iron in it. So clearly these stars, these exploding stars, can make that iron.
But hold on a sec. You were talking about a different type of supernovae earlier. Can they make iron as well?
Yes, indeed. It turns out those supernovae we talked about that me and others used to measure what the universe was doing back in time, well, they also produce iron. So in this case, we've never seen one up and close and personal like we've seen one in the Large Magellanic Cloud. Turns out Kepler saw one in 1604. I'm rather envious that he got to see one. They don't happen very often, so we're going to have to wait. But a schematic is that a little white dwarf star, like what was formed by our sun when it dies, or what will be formed, well, if it were to get heavier and heavier, it reaches that point of instability at 1.38 times the mass of the sun. It explodes, and the same type of nuclear reactions that create iron in exploding supernovae of the type 2, of the massive star type, happen in this as well. And we see in these things, we actually get a lot more iron, 0.6 solar masses of iron. So it turns out these are not as common as the first type, and so we're going to look next at figuring out how many exploding stars we need to explain how much iron there is in the universe.